So hi, I'm Sören, and today I'm talking about fault classification. So at the end of the talk, you will understand the definition on the bottom right, which is like the core idea behind our fault classification. So let's start with a little story. I'm from Braunschweig in Germany, and we have a company there. And like many companies, it's working for a big automotive company of the area, and they are tasked with testing. So they get ECUs, and they get a specification, and basically they check whether the ECUs follow the requirements, and they report back to the automotive company. Now, how do they do this? For this talk, we will assume a very simple requirements document. Basically, it says we have a variable x in the ECU, and it has the property that when you set it, it will be reset to 0 after 50 milliseconds. So that's the requirement. What they do is they take the ECU and they hook it up to the communication bus, and they plug in the testing environment. It's a protocol which is based on requests and responses. So they send a request to the ECU and say, okay, please set X to 5. And the ECU answers, okay, X is 5. They wait for some time, less than 50 milliseconds, and they send another request and ask the ECU what the value for X is. And the device says, okay, the value for X is 0. However, it should have stored the value 5 that we just set for 50 milliseconds, so this is a fault. Of course, they don't do this manually, but they have a bunch of people sitting there writing tests. A test is basically just a sequence of requests and expected responses. And as long as the device stays within the expected responses, it's not a fault. And if it gives a response that is outside of the expected response, it's a fault. Okay, so they send this test to the ECU, and they hook up to the bus and record what is happening. So what comes out of it is a trace. A trace consists of events, which are the requests and the responses. And there's also timeframes. So timeframes is the time that passes between events. So we're not doing absolute timestamps, but relative timestamps, as you will. I call them timeframes. So at the end, we will end up with faulty traces. And when we look at even a single ECU, which has a few faults, this can lead up to many tests failing in this company's testing environment. So it can easily go over 1,000 failing traces for an ECU. Of course, that's not acceptable. The automotive company will reject 1,000 traces. They will say, okay, give us few articulable faults, and we can go give these faults to the subcontractors so they can fix them and make the ECU correct. So the company doesn't have a real good way to do that. Instead, they just have a bunch of people looking at these traces, and they will look at a trace, they will find some fault, and they have experience, so they know which kind of other traces will probably also fail for the same fault. If you think of it, you have requests in each of these traces, and they might overlap. So you can see the same fault in many traces. Okay, and this is where we step in and we say, this is basically nothing but an equivalence relation on faulty traces. So we want an equivalence relation that groups together traces that have the same fault. And we would like to do so not by manpower, but by a computable relation. Okay, what do we want from our relation? Let's have a look at a few traces. The trace on the left is the one we already saw. The trace on the right has some additional events in the middle. Basically, it just has some logging events, and we would think that logging events do not really interfere with writing a variable and reading it back. So when we look at the timeframes that we have in the traces, both of them are under 50 milliseconds, and both of the traces return the value of 0 before the 50 milliseconds have elapsed. So it should not have been reset to 0, but it has. So we would say those are the same type of fault. Here's another trace. It also has log messages, but this time the request for getting back our variable x is later than 50 milliseconds. The device again fails for a different reason, probably because it returns 5, so probably it stored the value for too long. So we don't want to group these together, right? Okay, so this was the introduction. What we want to do is classification on faulty traces. In order to do so, we are not going to be able to handle a 300 pages normal language document. We need a formal model. And then we need to find our error, which is localization, And at the end, we want to reduce the size of our faults so that we can better compare them. Okay, we will start with the formal model. Okay, again, we stay with our simple requirements document, star x for 50 milliseconds. And we begin with the first part of it, star x, basically. And our formal model is automata. So we will stay with finite automata for the moment, and we will increase the power of our model step by step. This automaton has two states, the initial state and second state. And over the right, there's a copy of the initial state for better presentation. Our automaton should be able to read this trace, right? So it consists of events. In particular, we will first look at the set event. We just write transitions that read these events, and we're good to go, mostly. Because when we read the response, what we think should happen with the device is it should remember the value of x, right? So it should store it. So we equip our automaton model with a memory. And basically, we just have a set of variables that our transitions can update whenever they are taken. And then the automaton model remembers the value of 5 inside the variable, just as the ECU should do. Okay, we also have time frames. Now we at the star x part, we don't really care about the time frames. So what we do is we introduce a new symbol, delta. And whenever we see a time frame in our trace, we can proceed to taking a delta transition. Finally, we have the get events at the bottom. And we introduce new control flow to our automaton, where we proceed on the get events. The response for the get event is parametric in the sense that we have a value v there instead of a particular number. And basically, when we read a get event, we instantiate the transition with the correct value. Now, we're not quite done yet, because currently our automaton would be able to accept the whole trace, right? It shouldn't, because the trace is faulty, right? There's a 0 at the bottom. So what we do is we further enhance our automaton, and we add guards. Guards are checked at the beginning of the transitions. If they hold, we can take the transition. If they don't hold, the transition can't be taken, and the automaton might get stuck. So with that, the automaton would get stuck on the sequence, and we're happy. However, we are not completely done. We have to model the second part for 50 milliseconds, and we will do so in a separate automaton. Here's a blueprint. At the left, we have the initial state, and the top loop is basically just all of the events that can occur in the trace, because we don't really care. We just want to make sure when we see an event, we are in the initial state. There's also the transition that should reset x to the value 0. And basically what we want to do is we want to add a guard so that this transition will be fired after 50 milliseconds. We cannot do so yet because our automaton has no idea how much time has passed. And what we do is we introduce a second type of variable, clock variables, which are similar to timed automata. Whenever we take a delta transition, all clock variables are increased by the appropriate amount. Now with that, we can write a guard. So we want to reset the variable x after 50 milliseconds, and we add some slack for hardware. We also want to make sure that our automaton actually does take the resetting transition. So we will force it out of the initial state after 50 milliseconds plus slack. Now we have to do some bookkeeping. We have to reset our clock whenever we re-enter the initial state after resetting x. And we also want to start the timer whenever we actually see a set event. And with that, we are done. We just make the product automaton of these two, and we have our formal model encoded as an automaton. Okay. In general, how does it look? We have two types of transitions, delta transitions and event transitions, each of which can be equipped with guards and updates. And we have a memory and clock variables. So that's our formal model. For the semantics, we have configurations with state and assignment to memory and clock variables. Now we want to take a transition, and for the example, we do timing transition, a time frame transition, because they are slightly more complicated. And let's do it on a concrete example. So we have x is 5 and c is 48. And a concrete transition, this is the transition that resets x to 0. Okay, so the first thing that we do is, I said we increase the values for clocks by the appropriate amount. And that's the first thing that happens in a transition. The next thing that we do is we check our guard And whenever the guard is satisfied by the assignments, we actually can take the transition. If it is not, we cannot take the transition and we might get stuck or have to choose another transition. Finally, we can apply the updates to our configuration and we are done with our transition. Now, when is a trace part of our language? When does it follow the requirements document or is accepted by the automaton? We could go with initial states as we just saw and final states, but for this talk, we will just say start at any configuration. If you can process the trace and end up in some configuration, we're happy with the trace. It's accepted. The final thing for the model is that when we have consecutive time frame transitions, delta transitions, and we start in this example in a configuration in P, and we have a time frame, we would expect that our configuration afterwards can be either Q or S. And in the previous slides, we were not able to do so because each time event was just processed by a single transition. Basically, what we allow our model is to arbitrarily split and merge consecutive time frames in the trace. Okay, so that is our formal model. What we want to do next is we want to find faults within traces. So that's localization. When is a trace faulty? It is faulty when it does not belong to the language of the automaton. So the intuitive way would be to say, just let the automaton run. However, we said we can be at any configuration in the start, so we don't really know. And thanks to memory and clock variables, we have infinitely many states. So what we do is we do symbolic representation. In our case, each of these is a tuple with P, a state, and F, a formula that restricts the values for memory and clock variables. So a configuration is part of this set whenever the assignments satisfy the formula. Okay, now with that, we can go and do a Hoare proof on our trace. So we start with all configurations, true. And we do a strongest post condition and we land at our clock variable is bigger than 5. Now, this is a slight deviation from the previous slide. I said it's tuples from states and formulas. Now it's a little tedious to track all the states. We'll just write down the most important formulas, and whenever states actually do become relevant, I will tell you. After the first step, nothing changes with the formula, except for the state. We don't care. Next step, we increase our clock by another 2. Next step, we set x. Okay, we know x is 5. And we can continue on with strongest post conditions until we finally get a false after the last event, which is indeed faulty, and therefore we don't have a run on it. So we started with true, all configurations. We let our automaton basically run in a symbolic manner. And we ended up with false, so there's no run after the last event. Now we could say we are happy, we found a fault. But we are not happy, because this fault is the whole prefix up until this point. So we want a shorter trace that depicts this fault. What we do is we forget the proof up to this position, but we know the position. So what we do is we do a weakest pre-backward computation in order to find a smaller trace. Now, for events, this is basically standard weakest precondition. For time frames, we had to do a little bit of work. So we adapted weakest preconditions to be able to handle time frame transitions. It's basically, I'm not going to go into details, it's basically understanding time frames as a sort of assignment. Okay, but we can do it intuitively. We want to store x for 50 milliseconds, and our post condition is x should not be 0. We know after 50 milliseconds, our automaton model can reset x back to 0. So we have to make sure in the precondition that it cannot take that transition. And thanks to the guard, now it cannot. Okay, we continue onwards with the weakest precondition, and what we see is a whole prefix of the trace becomes true. We can just forget that because this is still a trace that is faulty, right? We begin in any configuration, we execute the trace, we end in false. This is still a false. Okay, so that was localization of false. We're still not happy. We still want to shrink down the size of false. Okay, here's the second example from previously, the one with the log messages. Our intuition was that log messages are not important when we are looking at storing a value x. And now we will show that they actually are not. So we do localization as before. And when we look at the Hoare proof and the assignments that we have, they all look rather similar. Okay, I lied to you because of the states, but the highlighted ones are in the same state. Let's look at this in a little bit more detail, but we are just forgetting the intermediary assignments. This is a valid proof. And what we do is we want to have the trace without the events. So we take the trace without the events. Remember splitting merging, we can merge them. Okay, simple trace. And what we want to do is we want to make a new proof for this part. We take the same post condition. We compute the precondition on the new trace. Friendly enough, it looks the same. Okay, that's good. Remember that those are sets of configurations, right? We don't need equality. It is sufficient if we have inclusion. Why? Well, if we have on the right side the bigger set of configurations, which are our precondition, well, a smaller precondition should surely work as well. So this is still a valid proof on the right. Now, when we go back to our trace, what we can do is we just remove these events. We remove we merge the timeframes, and we just showed that this is still a valid proof because the part that we changed is still a valid proof. Okay, so indeed, we have removed our log messages, log events from the trace, and we have further reduced the size of our faults. Okay, finally, we can go to classification, our target for the stock. Here are the two traces from the beginning. The upper one is the one where we only did localization to, and there was no explanation that we could do. The bottom trace is the trace for the log messages, where we did localization, and afterwards we just saw how to remove the log messages. So it's a short trace as well. And when we look at them, they are looking very similar again. Basically, when we look at these traces and we want to make them similar, we want to make them look the same. What we would want to do is we would just want to wiggle the time frames just a little so they merge together into a single proof. And this kind of wiggling of time frames, this is the part where we want to lay down our classification. However, we cannot do this too much, because if you would just go and wiggle the time frames so that you end up with more than 50 milliseconds, you would probably violate the idea of grouping together similar faults and end up grouping together faults that are not similar. Okay, so first let's make formal what wiggling time frames actually means. We will forget about one of the traces and look at the other. And what we do is we create a new trace. We copy the events, but we forget about the time frames. Instead, we just take time frames which have variables. Okay, we again do weakest preconditions. Our weakest precondition development also works with some symbolic time frames, so we can apply that as well. And when we look at the bottom trace, there's 3 milliseconds for the last time frame, and we insert it for U1. We would actually get the exact same assignment that we have on the bottom trace. And that's generally true for this approach. So when we complete the rest, whenever we substitute the variables by the actual values, we will get the concrete proof from the bottom. Now the shape here looks very similar between the template, this is what we call the upper thing, and the actual proof at the bottom. This has not need to be the case. Okay, the template can look more complicated depending on the automaton model that is behind it. Now, if we take our other proof that we have, and we would do the same thing, we end up with the same template. So we could think we have done it. We are ready when we have the same template. They are similar, but we are not. What we have just done is wiggling, because we just allowed any time frame to change arbitrarily. And we're not done yet. What we want to, and to show you that we are not done, we're going to do a small example. We have a slightly different requirement. This time we have the register X to be reduced every 20 milliseconds. We're not going to go through the automaton. Instead, we just look at traces. So here's a trace where we set X to 5. And after less than 20 milliseconds, we read back the value and it returns 3. So probably the device did something wrong. It did not return the 5 that it should have. Here's another example. Again, we set x to 5. We wait for more time this time. However, the device again returns 3, which is wrong because if we add up the time frames, we end up at more than 60 milliseconds. So it should have reduced the value 3 times by now. But it's just barely about 60 milliseconds. So it might be the case that the error that has happened here is that the device responds just a little slow, right? It read the value correctly and then in the way onto the bus and stuff. So maybe it just replied slowly. What I want to get at is we would not want to say that these are similar faults. They very well might have different reasons. They could have the same reasons, but it likely doesn't have to be. Now, when we build the proof templates, they will look exactly the same. And the reason for that is very obvious. When we have the same events, we have the same template. Okay, so we want to allow wiggling, which is what our template does, but we don't want to do it arbitrarily. So what do we want to do? So what can we do? We look at our template, and I've already highlighted all the atomic formulas where our symbolic time frames are occurring. So U1 and U2. We collect them and we call them atoms. Now the idea behind this is that when we do weakest preconditions and we get a new formula into our proof, a new atom, it is always the case that it stems from some kind of guard in our automaton. And guards is the only way of our automaton knowing whether it can take a transition or cannot take a transition. And this is what we base on our equivalence relation. We say two traces are equivalent if, and now we explain what this is. Set 1 of atoms is the satisfied atoms when we insert the actual time values into the atomic formulas. So we get a set of atoms where we use the actual time values of trace 1 instead of the symbolic time values. So the set of atoms basically splits into the ones that are satisfied, basically some guards that are satisfied along the way, and the ones that are not satisfied, so some guards in the automaton which are not satisfied by the trace. And we do the same thing for the trace 2. And if those sets are equal, basically our automaton cannot distinguish which trace it is seeing because the same transitions will be satisfied when walking through the automaton. And indeed, when we look at our traces that we want to have equal, we will get that they have the same set of satisfied atoms. Okay, so that is the classification algorithm. We implemented it in C#. We have a model which is a little bit bigger. And we would like to have a better evaluation, but we had some trouble getting traces in from the company. So basically, I can show you that we ran traces and in a reasonable time on my laptop. What we have observed in the traces that we got from the company is that the template length usually only has 2 events. So basically, somewhere you find an event that sets something, somewhere you find an event that checks something, and most of the time the middle part is not relevant. So that's a good thing because if you're a tester at the end and you look at your cluster that we get from our equivalence relation, they only have to look at a very, very short trace. We've also had some interesting parts. We found undetected faults. So the company did not find faults that we did. We found faulty tests. Basically, the testing environment thought, okay, here's an error. And we said, no. And what is also good is that the company never complained about our classification. So when we looked at different traces that we classified together, we never got back the answer that it should actually be a different faults, which is good when you're thinking about automotive software, right? You would not want to have a car where 2 faults have been classified as 1 and only 1 has fixed. Okay, so with that, we are done. We did a formal model, we did localization, explanation, and finally classification.
shall I take your mic and you can use that one? Super.
Let's go. What future work? We talked about how to verify booking conditions. So, differently often getting to some state of how you would then find the right traces and convince the company that this is actually happening.
So we have not. The most reason for this is that we went with a very practical project, right? And there a trace is always finite, right? You don't have infinite traces. So basically we did not have a reason to go for that way. It would be interesting to find a test trace that actually is infinite. I'm not sure.
Well, no, but it's important to go back to the state and then you can convince them that it's actually going to loop. Always a whole at the right state.
Okay, so you want to step forward from just looking at traces forward to actually doing verification on an implementation. Because currently we are using the device as a black box, right? We are only getting the traces out, and we are comparing them against the automaton model. So, yeah.
My question is about classification. You're using just an equivalence, and I was wondering if maybe you can't use them also using name. Maybe sometimes one fault is a general fault, and one fault is more specific. So if you take care of the general case, then the case will already be corrected, and therefore you don't need to take care of some of these sets of classifications with the more specific.
So you're talking about a refinement relation over equivalence.
Yeah.
Oh, okay.
Yeah.
We've also not thought about that part. Might be an interesting work. If you want, we can sit together later.
I had a question in mind. I guess I can almost use you to follow up that last question. So a lot of these examples were either like you were looking to what's the value decreasing and over time and seeing that it wasn't zero over time. Let's say, for example, the chip we're looking at, maybe one of the bits, the weights that are faulty. So sometimes
Can you a bit louder, please?
Okay. Let's say one of the bits is faulty, so sometimes the value you need back isn't zero, but it also isn't the number you're expecting based on the variable in your automata. So each of those things might look like a different fault because you're learning a value and reading back something different. So the proofs would look different possibly. But I guess part of that last question, those might look like they all belong to some classification of not reading back the value you learned. So with those kinds of problems, how would those be classified based on the approach described here?
Okay, I'm not sure I understand the question correctly. So I'm trying to repeat. So you're asking, what if you're not checking for a particular value, but you're looking for another kind of guard, which is failing, or?
So you have the same code here, but let's say the fault is sometimes like maybe one of the bits is faulty, so the value you write in isn't the value you read back.
Oh, okay.
So how would this classify each of those as a different fault?
Now, currently, you can go two ways, and we have done so in the implementation. So basically, the first thing you can look at is the events in the proof template, right? And do they match exactly? And you have the values in there, right? So I think that answers your question about what if the values are different, right? Now, you could also go the next way and say, okay, you don't require the events to be exactly the same. So then what we would do is you would only look at the assertions in the proof. You could do that as well.
Okay. I think that's
Any more questions? So one question I had was just a follow-up, I guess, from your implementation slide.
Yes.
So I'm wondering if you have any insight for kind of how things broke down at the company where these tests were faulty or they missed things. Kind of the insights into why things failed and your system can do better at. Maybe the black box, I don't know.
It's a tough question because I'm not sitting inside the company. They only delivered trace sets to us, and we had a hard time dealing with the trace sets belong to different requirements documents and stuff. So it's hard to answer the question really.
Yeah.
Maybe, does this influence the company to like all these specifications or because they now see value that you finding policy?
I hope so.
Yeah.
I'm actually not sure. The timing of the project was probably not perfect because COVID occurred and the company got cut by the bigger company by quite a margin. So I guess they probably don't have the time right now to implement. But I hope so.
All right.
Maybe I can actually answer one thing about this. So I took a look at the requirements token. We got that as well, even though it's classified, of course. And when I looked it out, I opened it. What I saw immediately is a finite automaton. So the broad concept of their specification is based on something that they can write down as an automaton. But afterwards, there's a list like, I don't know, 20, 40 messages about what the specific transitions should be and what should be happening. And right, so it's not perfect. And it's also mixed between the communication protocol, which is what we are analyzing, and the document as well at the same time specifies the inside of the ECU, what we cannot see from the trace, right? Because it's only on the bus. So there's still some mixture going on. So I wouldn't say this is close to a formal specification.
All right, thank you.